Have you ever wondered how we objectively compare something as complex and varied as different brain-computer interface systems? How do we move beyond anecdotal observations to a clear, measurable understanding of their strengths and limitations? A comparative framework for brain-computer interface, or BCI, assessment is a structured approach. It uses standardized metrics and evaluation criteria to systematically analyze and contrast the performance, usability, and safety of various BCI systems. This framework allows researchers and developers to objectively understand how different BCI technologies measure up against each other. The importance of such a framework stems from the sheer diversity of BCI technologies. Imagine trying to compare an invasive neural implant designed for motor control with a non-invasive EEG system used for communication. Without a common set of benchmarks, meaningful comparison becomes nearly impossible. This framework provides the lens through which we can assess everything from signal acquisition quality to decoding accuracy, and from user training time to long-term system stability. It helps standardize the evaluation process across different labs and applications. To effectively use a comparative framework, you typically begin by defining the specific BCI application, whether it is for motor restoration, communication, or sensory substitution. Then, you select relevant metrics. These might include bit rate for communication systems, which measures the amount of information transferred per unit of time, or classification accuracy for decoding tasks. Other critical factors include the signal-to-noise ratio of the recorded neural data and the overall robustness of the system in varying conditions. Finally, you apply these metrics consistently across the BCI systems you are comparing, ensuring controlled experimental conditions. A key concept within these frameworks is the notion of a benchmark dataset. This is a publicly available collection of neural data and associated tasks that different BCI algorithms can be tested against. Using benchmark datasets ensures that researchers are not just comparing apples to oranges, but are all evaluating their algorithms on the same standardized fruit. Another valuable component is the inclusion of qualitative user feedback metrics, which complement the quantitative data by capturing the subjective experience of BCI users, such as comfort and cognitive load. Ultimately, a well-defined comparative framework brings much-needed rigor and clarity to the rapidly evolving field of brain-computer interfaces. It moves us toward more informed design choices, accelerates development by highlighting areas for improvement, and ensures that the BCI technologies we create are not only technically impressive, but also genuinely beneficial and usable for the people who need them most.